Okay. Question. Tell me ways in which you use your home's water. Shower. Shower. Keep going.
Wash your hands. Dishwasher.
Washing hands. Washing dishes.
Sprinklers.
Laundry. Grass care. That's good. Okay. So in Canada, it's the government's responsibility for providing clean, safe, and reliable drinking water. Okay. And usually it's provincial that look over it, with Health Canada, the national one, sort of providing an overall supervision. Okay. Now, drinking water contains lead because most of the pipes that were used, and that's changing now, were lead pipes. So obviously some of the lead from the pipes was leaking into the water as it was coming into each home. Lead contamination, you can see here, can cause many medical issues. Okay, so there's a guideline to make drinking water safer. And, you know, this is a lot of, if they don't meet this guideline, and I'm sure you've heard this about different communities across Canada when they say, you know, you can't drink the tap water. Okay, that means that they haven't met this, likely. That there's too much lead in the water or something. There might be something else more, but I'm just talking about lead right now. And it must be for every 1 liter of water, 0.005 milligrams of lead or less. Okay. In the States, who's responsible for the drinking water? The states and the Environmental Protection Agency. They make regulations. And they have a lead and copper rule. And they say no more than 10% of households, I guess in a certain community, okay, can have prominent lead levels, which means, according to them, greater than 15 parts per billion in their water. So if they have 1 billion of water, 15 of those or less has to be lead and copper. Okay. So imagine if you didn't meet the rule and they said there's a risk of using your home water. Okay. I mean, how would your life be changed?
You can't use it at all. You can.
What's that?
You can't use it at all. You can't.
Yeah, you can't use it at all. So what would you have to use instead? You can't use any tap water. Or, I mean, there might be a boiled water advisory in which you can use the water, but you have to boil it. So we could include that. May have to boil water. But what if it's even worse than that? What would you have to use? Yeah, bottled water for everything. Imagine the crisis that would create. Everybody would be clamoring for bottled water, and you'd go through it like crazy. Okay? And this is what happened in a town in Michigan called Flint several years ago. Okay, over 10 years ago. And it was really created, it was a problem created by the government. Okay? And so what happened as a result of it, way too much lead and copper in too many homes. So tens of thousands of people in Flint were exposed to dangerous levels of lead. And one of the effects of that is something called Legionnaire's disease, which killed at least 12 people in Flint. A whole bunch of people got sick. Okay, and it was a huge crisis. So, and we're not going to watch the YouTube video, but it's just basically the government was denying that there was a huge crisis, but people were saying, no, there's an issue here. And advocacy groups were saying, no, there's a real problem here. And like there would be, you know, what was it? I have a picture here. We'll have it on the next page. Like they had, like there was a news anchor who was drinking. He's saying, oh, it's perfectly safe. And so he's got a cup of apparently Flint water that he was drinking on air, you know. So you had this whole group of people saying, no, there's no issue. And then you have this whole other group of people saying, yeah, we're getting sick. Okay, and there's a big problem. So how did researchers and citizens use stats to hold the Flint officials accountable? Well, what they did, there was a doctor from Virginia Tech named Mark Edwards. So he did something that we talked about last class. He randomly sampled homes in Flint. They tested each home's water for prominent lead levels, and they wanted to figure out what was the percent or proportion of homes in Flint by using a sample and applying it to the population that had too many lead levels or too high lead levels. Okay. And so what they did is they created what we talked about last class, a confidence interval, to find the percentage along with the margin of error, right? To say that, well, this is what we got as a percentage of homes, but it could be as high as this, or it could be as low as this. So if we were to sort of replicate that, and there is a place that you can go to where you can actually sample homes from Flint, and it will tell you, like you say, get sample, and it will say a home, and it will say whether it's prominent lead levels or not. Okay, so I'm just going to use some numbers here. Because I did it randomly, and this is what I got when I did it randomly. I got 18 of the 50 with prominent lead levels, which means 32 did not have prominent lead levels. Okay. That means our sample which was 18 out of 50, or 0.36 or 36%, had prominent lead levels, way above the 10%. Way above. Okay. This suggests a violation of EPA regulations. But is it proof? No, but not necessarily proof. Why? And this is usually the way you should answer this question. Not necessarily violation of EPA, but not necessarily proof. What could have happened? Yeah, right. We could have just got that by chance. We could have gotten a high result by chance, or gotten a high percentage. I'll just put high percent. by chance.
Would that be definitely variability of health or no?
What's that?
Would that be?
Yeah, it would mean the same thing, because different samples produce different results. Maybe we got that extreme result by chance, but we're just not sure yet, which is why we have to create a sampling distribution and run a simulation and do it several times over and see if the result we got is sort of the same as the sampling distribution. Okay? But yeah, basically means the same thing. Okay, so before we go about it, let's just remember what we're dealing with here. What's the population? Sorry?
All of them.
Yeah, all homes and flats. And what are we measuring? What do we want to measure all homes in Flint?
The percent of them.
Yeah, and I'm gonna say proportion, because usually when we do the actual math, we do it in proportion, not percentages. Proportion of all homes with, instead of prominent, I'll just put high levels. What variable name would we give to that?
You.
The proportion.
Me with no.
P with no hat stands for population proportion. The sample is the 50 homes sample. And the statistic is the proportion of homes in the sample. With high lead levels. What variable name do we give to that?
You and that.
P hat. Okay. Just to remember, and I want to keep sort of emphasizing this because I think there was a little trouble with Unit 6. In Unit 6, we knew this and we estimated this. But that's not the way things are done in life. The only reason we did that in Unit 6 was to show you the relationship between the two and show you the formulas that we can use. This is way more important, where we find this and we're trying to see if we can use it to estimate this. Okay, that's really what statistics is all about. We have a sample measure, and there's usually, it's either a proportion or a mean. In this case, it's proportions. And we're using it to see if it represents a population proportion or a population mean. But we're focusing on proportions right now. Okay, so in the last class, we substituted P hat for P in our sampling mean and standard deviation, and I'll just put STD, DEV calculations. Assume the conditions are met So in order to create a confidence interval, we would need the sampling distribution to be normal. Okay? We would need the sample to be taken randomly, which allows us to state that the average of the sample proportions that we took, because we did this thing over and over again, okay, is the same measure as the sample proportion we got from the one time that it was done. Right? This is what we got the one time it was done. This is what we're going to get if we do it several times over using a simulation and average them out. The standard deviation, but there's a change now. Because we are going in the other order, we don't call it the standard deviation, and this is just words. This is just the vocabulary that's used. Okay? We call it SE of the sampling distribution, and that stands for standard error. So we don't call it sigma of the sampling distribution. We call it the standard error, but we still use the same formula. The square root of the sample proportion we got times 1 minus the sample proportion we got divided by the sample size we took. So in this, using our numbers, normal, what will be the average of the sampling distribution? What value?
0.36.
0.36, correct. It will be the same as the sample proportion that we got from the one actual sample we did. The standard error is going to be 0.36 times 1 minus 0.36 divided by 50, because that was the sample size, and then take the square root of that answer, and that gives you approximately 0.07. Hopefully you have enough room. All the data in here represents all the sample proportions we got when we did a simulation. So, you know, maybe we did one simulation, we got 0.40, so it'd go over here somewhere, and then we got 0.33, so it'd go over here somewhere, and however many times we did it. We fill all this in, and it takes a normal shape with a mean of 0.36, and all the other values will be +1 standard deviation, +2, +3, -1 standard deviation, -2, -3. So I've got to add 0.07, so I get 0.43, 0.50, and 0.57. When I subtract, starting from the mean, I get 0.29, 0.22, and 0.15. Sorry, I should have put that sample proportions label lower. Okay. Right now, the only confidence interval that we can create is a 95% one, right? Because we know how many standard deviations in a normal distribution, what air, like how much 95 represents. It's 2 standard deviations away in either direction. So 95% of the data will be between this notch and this notch, which represents our confidence interval. But I hate to throw this to you, it's not exactly 2 standard deviations. I've lied to you. 2 standard deviations does not represent 95% of the area. 1.96 does. I know, it's really close, which is why we say 2. Okay, and I feel badly for lying. Okay, but I wanted to keep things easy to start. I did it for you. I tried to, because I cared about you. She's not even looking at me. She's just like playing with it. Well, it's better than doing this. Okay, so technically it's 1.96. So we go just a little inside, just a little inside. And that represents 1.96 standard deviations, but remember we've called it standard errors. And 1.96 that way. So how do we figure out these little values that are really close to 0.22 and 0.50, but a little bigger than 0.22 and a little smaller than 0.50? We use the confidence interval formula. Okay, and if you remember that confidence interval, and I'm just going to call it CI, is the point estimate plus minus the margin of error. So our confidence interval, 95%, we know the point estimate is 0.36. We need to figure out the margin of error. How do you figure out the margin of error? You take the number of standard deviations, okay, times the standard deviation. So like this is 2 standard deviations, right? So to figure out that, I just go 2 times whatever that is. The standard deviation is 0.07, but it's 1.96. So instead of 2 times 0.07, it's 1.96 times 0.07. Because 1 standard deviation is 0.07, and we're going 1.96 standard deviations in either direction. So if we figure that out, if you do 0.36 plus the product of those 2 and 0.36 minus the product of those 2, here's what we get. 0.2228 to 0.4972. What does that mean? Well, that means applying it to the population, 36% of the homes in Flint had prominent lead levels, but it could be as low as 22.28%, right? Because of the margin of error, or it could be as high as 0.4972 or 49.72%. That's the confidence interval. Well, that kind of tells you something. Okay, think about it. What was the percent? What was the mandatory percent? 10%, right? Less than 10%. Okay. Would you say, yeah, actually, it's above the 10% level? Why? Because all the results we got 36%, right? But the margin of error makes it as low as 22%, which is still well above 10%. This is way above 10%. So all the possible values we got are all above 10%, which suggests, oh yeah, definitely there's a violation of EPA rules. So that's the conclusion we would make out of it. Okay? Now, something we're going to use for the remainder of this unit and the next unit. How to answer these types of questions. So we're going to revisit this. And I'm going to show you how we would present the solution. And it's called the four-step process for inference, because that's what we're doing. We're drawing conclusions now. Okay? First one is to state, what are you going to be doing? Second one is to plan, okay, what's the inference procedure I'm using, and are the conditions met? The third stage is the do part, where the math takes place. And the fourth stage concludes, answer the question being asked. Okay? We're going to do tons of these, so you'll get used to them. So this is the type of question you would see. You would be given information about Flint, and you would be asked to do this. Construct and interpret a 95% confidence interval for the true proportion of Flint's homes that have prominent lead levels. After being told the sample size, that it was selected randomly and 50 homes were sampled, and the sample proportion was 0.36. Okay? So to state, you basically restate this sentence. Okay? Constructing a 95% confidence interval, and I'm just going to use CI. Confidence interval, just remember that. So the true proportion of homes, true proportion of Flint homes. True proportion, what missed words of Flint homes. So the confidence interval question will state, like I said, you're really restating the one instruction you're given. Plan. What are we going to do? We are going to calculate maybe one sample, because we're taking one sample. Now I'm going to use a letter that we haven't seen yet, but this will be explained in the next lesson. So we are going to calculate a one sample Z interval. When we do a confidence interval for proportions, we call it a Z. For means, we call it a different letter, but that's unit 8. That's well off. Okay. For the true proportion. So for P, without the hat. If conditions are met. Here's where the three conditions come in. What are the three conditions with proportions? Random, 10%, large counts, good. So, random. That's easy. We were told. Homes randomly selected. Check. %. Flint is a fairly big city, so it has way more than 5,000 homes, or 500 homes, because it would have to have less than 500 homes not to meet the 10% condition, right? Because we took a sample of 50. So we would say 50 homes. Less than 10% of all Flint homes. Check. Large counts. This is where we have to do two calculations. NP and N1 minus P. They both have to be greater than or equal to 10. So NP is 50 times 0.36, which is 18. That's good. Fifty times 1 minus 0.36, or 0.64, gives me 32. That's good too. Both greater than or equal to 10. All our conditions are met. I'm running out of space. So I write too big. So I'll have to try and squeeze it in here. Do. Well, this is where we do the calculations that we did on the last page. Okay? So remember, how do we find the confidence interval? It's the sample proportion. And for 95% confidence, that's 1.96 standard deviations, times whatever the standard deviation, remember we call it standard error, of the sampling distribution was. And from the previous page, this was 0.36. We calculated this to be 0.07. You'd have to show your work how you got 0.07, but we showed it on the last page. Okay, so you'd have to show how you got this. And then you would get 0.228, comma 0.54972. Finally, to conclude is where we have to do a sentence. And we would phrase it this way. We are 95% confident the interval, and then state the interval that you got. 0.228 to 0.4972. Captures the true proportion Flint, I'm gonna say Flint homes. With high lead levels. That would be considered a complete solution. Okay, state plan do conclude spiders prefer dark corners. Okay. User it, and we already answered this question. Yes, because every possible proportion in our confidence interval, in our CI, is above 10%. So yes, it does violate. And that's essentially what this doctor from Virginia Tech did. Okay. And he got a confidence interval. It's in the discussion. What did he get? He got a little over 12% to 21%. And he did his. Okay. Which still, all of them were above 10%. Okay. And they finally addressed the problem. And I'm not going to worry about the discussion. You can read it at your leisure. Okay. But here's the thing. We're going to get to the point, and that's going to come up next. This is done in one step on our graphing calculator. You will go onto your graphing calculator. You will find where it says Z interval, one sample Z interval. You will enter that. You will be asked to enter some information, and it will spit out this confidence interval. So you can do it. So I'm going to, like, for every time we do it, different scenarios, I'm going to show you the long way. But then everyone has a shorter way for the do calculations by using the graphic. Okay. And either one is acceptable. Although what I hear from former students in stats is they say they don't use graphing calculators in university stats. That everything is done by hand, like this. Or instead, they use tables instead of a graphing calculator. So it gives you a whole bunch of information in tables. That's the way sort of stats used to be done. But graphing calculators helped us sort of make things a little bit easier. Okay.